Hi, in this video we shall see how to create layout for the inverter. There are different methods of creating layout and since you are in the beginning stage, we shall see the most easiest way of creating the layout. Here all the instantiation will be done by the tool itself. We just need to draw the metal wires. That's it. So we shall see how the tool is going to do that. So for that, first you need to click on connectivity, then click on incomplete nets, and then click on generate, then click on all from source. So connectivity, generate, all from source. So this generate layout form will appear for you. Okay, so here it is going to show all those things that is going to be generated by the tool itself. So instances means your pfet and fet instances that is there in the schematic, it is going to be generated. Then IO pins, your VDD, VSSV and Vout pins are going to be generated, and then PR boundary. So PR stands for place and route boundary, and there is a particular reason why we want this. Generally, for each layout, this is the kind of boundary that has to be drawn, reference line kind of boundary. Okay, so then if you go to IO pins, here you have all these things. As you can see, VDD, VIN, Vout, VSS, these are the pins, right, that we had in our schematic. So and the layer is M1 drawing. Let us have that those purpose should be pin. So I will be deleting that drawing. Instead, I will type pin. So it started appearing. Then I will press enter. So I also wanted labels to be created along with the pins. So I'll check this and then go to options, and then height, let it be default 0.02, and let the font be uh, Roman. So for better visibility, I'm choosing this Roman. You can choose any of the fonts, So I always recommend using Roman for pin names because it has a better visibility. And then you can keep layer name same as pin, and layer purpose same as pin. Justification and orientation, you can keep it default, and then click OK. So then you have some options for PR boundary. So the origin is 0 comma 0 here, and 0 0.0 and 0 0.0. This is x comma y origin. This will be the left bottom corner of the PR boundary that you will be drawing. Then you have floor plan. So as of now we are doing simple layout for this is just for inverter, so you can just ignore this part. You can skip that part as of now, since we are doing a very simple layout. Okay, then click OK. So now you can see all the instances have been instantiated, pfet, nfet, and they are having three fins. You can see one, two, three, similar to the schematic. What is there in the schematic like this? You have three fins, and for n fin you have number of um, fins for nfet is two, and you have two like that. So now what we have to do is we have to just connect the terminals. That's it. So we will be doing that now. So press F. So sometimes it so happens that PR boundary is not selectable. Like this, it won't be highlighting. Sometimes it happens like that. For that, what you have to do is just uncheck this and type here PRB. So probably this should have been unchecked for you. So just in that case, as you can see now, yeah, it is not highlighting. PR boundary is not highlighting. So just check the selectability for PR boundary. Now it is highlighting properly. Okay, so we need that because we will be reducing the overall area PR boundary. Okay, so for that we need to have the selectability for PR boundary. So now we'll delete this thing in the filter and click on used. So now you can see all the only the used layers are appearing in LSW. So all the unused layers are not present here. Okay, so now what we will do is uh, we shall see what are all the options are there for these instances. Select this instance, press Q for properties. Always remember, for any of the instances, or if you want to see properties of any of the things, you just have to select that particular thing and press Q. Then the properties will start appearing for you. So here you can see instance PM0 P1 SVT. It is showing all the attributes. Here you will be having cell view library of that instance, and where it has been placed, that information here you have, and this is your orientation. Will get let you know what exactly R90, R180, MXMY and all in further videos. So then you have a parameter. So here you can vary the number of fins and number of fingers here if you want to. As of now, it has a required number of fins and fingers, so I won't be changing those values. Now I will click on show layout parameters, and I wanted to keep uh, let us say this is my actual poly, right? And these two are edge polys, and these two are right and left dummy polys. So let us say I don't want the dummy polys. I will just make it none. So you can see the dummy polys are gone now, and say the edge polys I wanted it to be having like drawing only. So now you can see the edge polys have become drawing. So I will keep it um, as of now uh, drawing only, and edge polish and drawing only, and then left edge poly and right edge poly, and I'll keep it none for left dummy and right dummy as of now, and click OK. Similarly, I will be doing the same thing for NFET. So I have now PFET and NFET ready. This yellow color layer is the P implantation. Here the red color layer is the N implantation, and the violet color one is the N well. Okay, so you can individually switch on these layers and you can see. So this is your fin area. As you can see, these two are or the only two fins. So you have only two fins. These are you always need to ignore the fin area at the edge. So fins will be formed only in the where the active area is present, right? So these two are the fins. So, and this is your dotted line is your fin pitch line, that is coinciding with your this line, right? This line. Similarly, here you have three fins. Then, if I uh, open poly, this is your poly, right? So you can see polys are there, and there is actually cut active. So you can see we have cut active at the edges. Why? Because so it should avoid the formation of transistor. As you know, whenever poly crosses the active area, there will be a formation of transistors. That should be avoided. Okay, so um, we have edge polys for a particular reason to uh, avoid overetching of the actual poly. We have that edge polys actually. That is the reason. So, but at the same time, we need to have so at the same time, we need to avoid the formation of transistors because of the edge poly. How do we avoid the formation of transistors? We need to remove the active area at the edges. And how do we indicate that we need to remove those area by using cut active layer? And that's why we have cut active layer drawn exactly over them. Okay, so over the edge polish. So here you can see the cut active has been drawn. So uh, what I will do is there is one more thing that you need to observe. This is if you select the PR boundary and then click Q, this is actually your PR boundary. Okay, object. This is actually not a layer. So here you can see it is not appearing over here. So you need to create that layer as well. Okay, so first I'll click on unused, then go to PRB and then boundary. Then I'll enter into rectangular mode. I'll enter into rectangular mode by pressing R. So you can see the mouse pointer, and now I will click and release the left mouse click button here. So now my mouse is freely moving. I'm not clicking and holding I'm not holding my left mouse button and dragging. I'm just I chose the origin to be the my starting point, and I have uh, clicked and released. Okay, now I'm dragging my mouse towards the other end, and I need to stop my PR boundary here. So I'm keeping my mouse pointer here, and then I will press it again. So now I have drawn PR boundary. So I will delete this PRB here and click on used. Now you can see the PRB started appearing here. Okay, till now it was not present because it is not a layer that was there. It was actually the thing here, create PR boundary, and this PR boundary was present. Now you have already drawn the layer also. So you need to do both PR boundary layer as well as PR boundary object. This PR boundary is PR boundary object, and this is PR boundary layer. You need to have both PR boundary layer and PR boundary object. So I will enable all the layers now. So now we will see how to connect these gate and source and drain terminals of the PMOS, PFET and NFET. For that I will start with gate terminal. So I'll take path. So the binding key for path is P. Now I will start joining. Yeah, as you can see, I just moved my mouse near the edge. It started showing, it started highlighting here, and I will just click and release my left mouse button, and then I will just drag my mouse freely, as you can see here, and I will just bring it here near this edge and press enter to cut the poly there. Again, I will do the same thing for this one. Here, no such edges are present. Okay, so I'll just hit and join it. Similarly, I will do the same here. So this is done. So what I will do is I will select the entire instance like this, and I will move it towards left side like this. And so now what I will do is I will I have joined the gate terminal, right? So I need to connect this gate terminal to the input. Um, for that again I'll take the path P, and I will bring it near the edge and click and release my left mouse button and start dragging it towards the gate like this, and I will stop it here because this is my actual poly that I need to connect. Now these two uh, layers are crossing. Poly is one different layer and then M1 is one different layer. They need to be connected together. For that, to connect two different layers, we need to use via. So the bind key for via is click O, and you need to choose M1 to LIPO, right? Click on M1 to LIPO and then click on hide. Then you will be having this wire and keep it in such a way that the center of the wire is coinciding with the poly pitch line. So you have this middle line of the poly, right? That is called poly pitch line. That should coincide with the center of wire like this. Okay, so now I need to do uh, the thing, same thing for my output. So I will just keep it output here, somewhere here. Because I need no, I cannot write here, right? So my output is what? I should short the drain terminal of PFET and NFET, and this layer is called actually the LIACT, local interconnect active layer. So I need to short this LIACT. For that, I will be again using path P, and then bring your mouse near the edge of the LICT and then bring it down like this, connect it like this and press enter. Press F. So now I can say that my drain and drain are shorted. Now I will enable all my layers like this. So my drain is shorted. Drain of PFET and NFET is shorted. My gate terminal is connected to the input. So now I am good to go for joining my output connection. Again, I'll take a path and bring it near the edge of the uh, pin like this, and then I will use this. So here, as you can see, the moment I bring my mouse near LIACT, via is appearing automatically. If it doesn't open automatically, you can put the via M1 to LIACT in the similar way, like how we put M1 to LIPO. So I will just bring it here and press enter. So in case if it didn't appear, you can just press O and go here and click on M1 LIACT like this and press high and keep it like this, such that the via center of the via is coinciding with the pitch line of the LIACT, this middle line of the LIACT. Press F now. So now I need to connect my VSS and VDD pins. So VSS and VDD pins are connected to what? Source of the PMOS is connected to VDD and source of the NMOS is connected to VSS. And also you might be knowing that the body terminal is also connected to VSS for NFET, and body terminal of PMOS is connected to VDD. So what is body for NMOS? It is Yanval, right? So now what about PFET? The body for PFET is your P substrate. So this entire black screen itself is your P substrate. So for that we need to add tabs. So we will be adding NVL tab. Click on hide for your NVL. Keep it in a way such that the NVL is continuous. Okay. So now this is done, and similarly add a sub tab hide to you along with your infat like this. And then now what we will do is we will keep our terminal, we will keep our pin VSS and VDD pin on the tabs itself, and then join this metal with the LACT of PFET here, and the LACT here present will be shorting these two. Okay, so again I'll take the path P, and again I'll take the path P and bring it here, and as you can see the wire is appearing again automatically. Press enter for that. Again I'll do the same thing here. press enter for that. So now my source is actually connected to body. These two are shorted, but still both are not, both are shorted. Body terminal and source are shorted, but they are not connected to VDD8. For that, I'll bring this pin here. Select this. To bring it there, you have to move it, right? So first select the pin and press M to move it. Move it towards left first, and then move it towards down, and keep it in such a way that it is exactly coinciding with your V0. It's not a rule that you need to coincide your pin exactly with via 0. It's just the convention that we follow here. So similarly, I'll keep VSS in the same way. First, I'll select the VSS and then click on M to move it, and then I'm moving like this and keeping it on the sub tab, and then I'll just align it properly with V0. So now you have everything, and all the terminals and all the pins are connected. All the terminals of the instances and the pins are connected, but still you can see a lot of space are available here, right? We actually don't and we are not actually using that space, and PR boundary is drawn. That means once you are instantiating this layout in some other layout, so no other layout can come inside the PR boundary of this layout. So you are actually wasting this area by keeping it empty. So what we have to do is we have to reduce my uh, we have to bring this side of the PR boundary towards nearer, such that it occupies how much our area it actually requires. Also, we can bring this entire thing down, right? We are simply wasting a lot of area here again. So I'll bring it down like this here, and yeah, now you can see how much area I'm actually reducing, and then um, I will first move this, select, and then I will move it here and keep it exactly on the wire like this, and then I will just delete this metal. So I have the um, wire here, and above that wire I have already placed the pin. So now I have to reduce my PR boundary. So for that, what I can do is I can enter the coordinates of this directly, right? I can just select this PR boundary and press Q and go and edit the coordinates. Instead of that, what I can do is I can select this layer and bring it down, and select this side, sorry, this side, top side, and bring it down, and select the right side and bring it towards left, correct? So to do that, first you have to enable partial select. To enable partial select, you have to click F4, press F4 in your keyboard. Now partial select is enabled. So now you can see the difference. Now only the right side is getting selected, and here you can see only the top side is getting selected, not the all the layers. If I have enabled full select, again pressing F4 will make you toggle full select. So now you can see entire this thing PR boundary is getting selected. So press F4 again. Now we are in partial select mode, and now I will just select this, and um, I need to stretch this, right? Stretch it to this point. So yes is the bind key for stretching. Press yes and click on the boundary like this and bring it towards left side and keep it like this. So this is your boundary. But again, you can see there is one more here. As I had mentioned earlier, so this there is one PR boundary layer and there is one PR boundary object. So you need to bring both of them and keep it here, right? So here, similarly, you have to do the same thing in top. So instead of selecting one by one, what I will do is I will draw a selection box like this, and then press yes, and then bring it down like this, and then press F. So now I have all my PR boundary, everything is proper, and my layout is actually finished. Then press save. F2 is for save, or you can click on the floppy disk icon. F2 is the bind key for save. Press F, fit to window. So now I have my layout drawn. So I don't know whether it is DRC and LVS clean, but yeah, as of now, as compared to schematic, all the connections I have done and all the pins I have drawn, so maybe it is correct. To ensure whether it is proper, I have to run DRC and LVS and check whether it is clean. If there are any errors, we need to debug that. We shall see that in the next video. So that's all for this video. Thank you.